Hello everybody. This lesson is about the unit circle and was completed by Asher Palmer, Lauren Vanderhorst, and Nicholas Blackford. The prerequisite knowledge that will be needed for this lesson are special right triangles, the coordinate plane, and trigonometric ratios. So, the first question we're going to answer is, what is the unit circle and why do we call it the unit circle? Clearly, by the name, we are going to be dealing with a circle. We are interested in finding some points that lie on the circle, so we're going to put the circle on the coordinate plane. In the coordinate plane, we have both the x-axis and the y-axis. Now for the reason that we call it the unit circle. The unit refers to the radius of the circle. In order to make the math as simple as possible, we're going to make the radius of our circle 1 unit. Because the radius of the circle is 1 unit, we can find these 4 points very easily. The point to the right is 1 unit to the right and 0 units up, also known as 1 on the x-axis and 0 on the y-axis. Here it is 0 on the x-axis and 1 on the y-axis. Here it is -1 on the x-axis and 0 on the y-axis. And at the bottom it's 0 on the x-axis and -1 on the y-axis. In order to find other points on this circle, we're going to investigate the triangles that are used and made by the x and y coordinates. Since the radius of the circle is 1, the hypotenuse of the triangle is 1. Therefore, we can get that the cosine of the x angle is x over 1, which equals x. And the sine of the angle is y over 1, which equals y. Similarly, the tangent of the angle is x over y, which is the sine of the angle over the cosine of the angle. It is important to note that the unit circle is a tool that will help us to know the sine, cosine, and tangent values for specific angles. Since we have investigated special right triangles already, we will be looking at the angles that make up these triangles. It will be a 30-60-90 and a 45-45-90 triangle. Therefore, we are going to be looking at 30 degrees, 45 degrees, and 60-degree angles. Recall, when working with trigonometric ratios, we are interested in finding the ratios of the sides of the triangles that we have created. Thus, we are going to be looking at the 30-60-90 and the 45-45-90 triangles, each with a hypotenuse of a length of 1. Let's first look at the 45-45-90 triangle. Recall that the side lengths in a 45-45-90 triangle are the ratio of a to a root 2. Thus, we can solve for a by setting up the equation root 2 times a equal to 1. By solving this, we have a equals 1 over root 2, which equals root 2 over 2. For the 30-60-90 triangle, we have the hypotenuse of 1, and the ratio of the side lengths are a to a root 3 to 2a. Thus, solving the equation 2a equals 1, we have that a is equal to 1/2, and a root 3 equals root 3 over 2. Now we will switch to Lauren and she will discuss how this relates to the unit circle.
Now, if we go back to our unit circle, we can insert these 30-60-90 triangles to find the change in x and change in the y variables of the point that we are looking for. Using the side lengths that we just solved for, we are able to see that cosine of 30 degrees is root 3 over 2, and sine of 30 degrees is 1/2. By dividing sine by cosine, we can get that the tangent of 30 degrees is root 3 over 3. Using the same 30, 60, 90 triangle, we can derive the values for a triangle in the second quadrant. Now, when looking at the angle measures of the resulting point on the circle that we are looking for, we measure the central angle from the x-axis to the radius that connects to our desired point. Therefore, the angle that corresponds to this triangle is actually 150 degrees. When looking at the cosine value of this triangle, the adjacent leg has the same length as before. The direction of the leg, however, is in the negative x direction. Therefore, the cosine of 150 degrees is negative root 3 over 2. Since the y-coordinate of this point is still positive, we have sine of 150 is 1/2. And tangent is now negative root 3 over 3. We can use a similar technique to find the sine and cosine values for a 210 degree angle. Since the x and y coordinates are both negative, we have cosine of 210 is negative root 3 over 2. Sine is negative 1 over 2. And tangent is a negative divided by a negative, which makes it positive root 3 over 3. Similarly, for a 330 degree angle, we have cosine of 330 degrees is root 3 over 2. And sine of 330 degrees is negative 1/2. Therefore, tangent of 330 degrees is negative root 3 over 3. Using the same technique, we can find the coordinates of points that correspond to a 45 degree angle. Recall the side lengths of this triangle are each root 2 over 2. Therefore, both sine and cosine of a 45 degree angle are root 2 over 2. Therefore, since sine and cosine are the same value, tangent of 45 degrees is simply 1. Using a similar technique as the 30 degree angle, we can move the triangle to the second quadrant and find that the cosine and tangent values both become a negative click due to the flip over the y-axis. By flipping the triangles over the x-axis, we find that the cosine, sine, and tangent values will become negative when appropriate. Therefore, we can find the trig values for the 225 degree and 315 degree angles. Using the same method, we can use a 30, 60, 90 triangle to find the trigonometric values for a 60 degree and 120 degree angles. This also works to find the trigonometric values for 240 degree and 300 degree angles. Thus, when we compile all of this information into a single graphic, we have the unit circle. You can see that the coordinates of the points are equal to the cosine and the sine values of the related triangles that we derived. You can also see that each quadrant is identical, except for the fact that some of the coordinates are negative. Therefore, if we are able to remember the coordinates of the points in the first quadrant, by using the sides of the special right triangles we discussed, then we just have to think if the new point is in the negative or positive direction for the x and y axes. Lastly, you will notice that next to each angle, there are fractional values of pi. These values are called radians, and they are another measure of the angle. We use radians to measure the distance around the circle that we have traveled from the point 1, 0 to the point that we are finding the coordinates for. In other words, the radian measure of a central angle of the unit circle is equal to the arc length. Now, to find the conversion factor, we have to recall that a whole circle consists of 360-degree angle. Also, the distance around the whole circle is 2 pi r. Therefore, we can say that a 360-degree angle is equivalent to a 2 pi radian. Therefore, when we are trying to convert from degrees to radians, we will use this conversion factor. For example, if we are trying to convert a 30-degree angle to radians, we will put 30 degrees over 360 degrees is equal to our unknown radian measure over 2 pi radians. By multiplying both sides of this equation by 2 pi and reducing, we find that the radian measure of a 30-degree angle is pi over 6. In a similar fashion, we can find the radian measure of each of the angles listed. Radians are important for further studies in math because they don't have any inherent units, such as degrees. Therefore, when we are looking at trigonometric ratios in future applications, such as graphing and finding derivatives in calculus, we have less converting to do. We are left with the unit circle that you see here. The unit circle is useful in helping us to remember trigonometric values for common angles. When we learn other methods, such as the half angle, double angle, product to sum, and sum to product formulas, we will be able to find even more trigonometric values for other angles. This will help us as mathematicians to be less reliant on calculators and make us more efficient in our work. I hope this helped in your understanding of the unit circle.